Maritime Made on Eastlink TV, presented by Nova Scotia Business Inc., because great things are happening.
At 4 Deep in Dartmouth, Nova Scotia, they're using innovative technology to develop microscopes for liquid environments. Environments like the ocean, in manufacturing, in the oil and gas sector, and the wine industry. This particular holographic microscope is called a filter scan unit, and it uses holographic technology to check filters used in the winemaking process for yeast. To begin building the microscope, the technologist connects himself to a grounding strap. This eliminates the possibility of static electricity damaging the electronics in the unit. The technician assembles the frame using screws and a hex key. An additional tool is used to add some extra torque, ensuring the screws are nice and tight. Each piece of the frame is built up in the same way. The microscope frame is made from anodized plate aluminum, a material known for its rigidity and lightweight.
Once the frame is complete, the front panel is secured. Next, a stepper motor controller is mounted with bore screws. The stepper motor controller controls the motors on the XY aperture stage and how and when it moves. The stage is the moving part that will hold the liquid sample when the unit is in use. It moves on two axes or in two directions, X and Y. It's the next thing that's attached to the frame. Cables on the back panel provide power to the stepper motor controller. Two gray communications cables are attached to the XY aperture stage and to the back of the stepper motor controller. The XY aperture stage now has power, and it's moved into position to allow the technologist access for the remaining screws to be installed. The cables are removed to allow for further assembly and will be reattached later. The main circuit board of the filter scan unit is a power driver. It supplies power to both the camera and the laser inside the unit. The power driver also allows the camera to pulse the laser with each frame. It's screwed in place. The fiber optic cable that produces the laser light for the microscope is inside the laser housing. The laser light comes out of the white end of the cable, or the ferrule, that holds the laser light in place. A spacer and a mounting plate are used at the end of the fiber optic cable.
While being careful that the top of the ferrule doesn't touch anything, the laser housing is placed inside the center of the frame. Screws are secured by hand, then tightened into place. Then the laser is connected to the power driver. The top plate is mounted next. The unit is turned so the cables can be attached. The communication cables between the stepper motor controller and the XY aperture stage are connected. These cables power the camera, control the pulsing of the laser, and will be connected to the power driver. The back panel is attached and control switches are connected. After the wiring is complete, the bottom cover of the unit is attached. The unit is turned right side up to mount the camera. The camera is held onto a mounting plate with a 5-axis gimbal, which allows the camera to move in many directions. This camera doesn't use a lens. Instead, the unit collects the optical information that hits the camera's image sensor, and that information comes out of the camera and into a computer as data. High-precision ball-bearing trundles allow the user to move the camera back and forth so that the sample tray can easily be inserted or removed. A connector from the power drive is attached to the camera. Then the Ethernet cable is connected.
The Ethernet cable is how the microscope communicates with an attached computer. A handle is installed on the trundle for gently handling the camera. A lid covers and protects the entire unit. The sample tray fits into the top of the XY aperture stage. Filter scan units are used in the wine industry to ensure that there are no live yeast cells left at the end of wine production. Live yeast cells would continue to spontaneously ferment, changing the character of the wine, or even worse, leading to a product recall. Today, Devonian Wineries of Malagash, Nova Scotia is testing a recently bottled wine. To begin testing, a funnel is removed from a flask. A specialized filter is selected and placed on the filter holder. And the funnel is put back in place. 100 milliliters of wine is poured. A vacuum pump is turned on. This pump pulls the wine through the filter. A glycerol mixture is also run through the filter to make it transparent for the filter scan. Then the filter is removed and placed in a petri dish. A clear cover slip is placed on top of the filter. The dish is then placed onto the sample tray. As many as 4 filters can be loaded at a time. The tray is loaded into the filter scan unit directly above the laser and directly under the camera.
4Deep's proprietary software analyzes the data and looks for any living yeast cells. The test creates cell counts and a library of holographic images that can be explored by the tester to learn much more about the sample. The tester can select 2D image slices from the liquid tested and look through the holographic images of that liquid. Testing for live yeast in wine traditionally takes 4 days in a laboratory while waiting to see if yeast colonies grow on the filter. This testing is done right at the winery and only takes 15 minutes. Another type of microscope made at 4Deep is a cuvette holographic microscope. It's made for use in educational settings. This design uses a small, high-quality camera fixed precisely in line with a laser that is fused to a very small fiber optic cable. Here, a liquid sample is measured and placed in the microscope. The microscope connects to a computer where the data is displayed. Holographic images are produced and recorded. Then the software analyzes the images. Microscopic organisms can be seen from as small as 2 microns or 2/1000ths of a millimeter. That's pretty tiny.